In this example, we're given a circuit that contains a capacitor connected to this part of the circuit, and at time t equals 0, we have a switch that flips from position A to position B, connecting that capacitor to a different part of the circuit in here, and forming an RLC in series circuit with a voltage source in here. And what we're being asked to compute is the voltage across that capacitor and the current flowing through it and through that inductor, since it's a single loop in here. So I'll start off by writing the differential equation that describes this particular circuit, and what you see in here is the following. We have just a single loop circuit in here. We can simply just write KVL across it around this particular loop, and if I assume that the voltages across them are of this particular polarity, so that it makes my passive sign convention things easier, what we have is we have the following. We'll get negative 100 plus, well, what I care about is the voltage across that inductor. However, we know that the voltage across an inductor, VL of t, is just simply L times di of t divided by d of t. Okay, and that's based on passive sign convention. The current is flowing this way, it's hitting the positive, so positive is okay. What about the value of L? Well, the value of L in this particular case is 5 millihenries, so let me just do that. Okay, so what we need to do is we need to write 5 millihenries there, and there you go, that's 5 millihenries. So we can just substitute it in here. That becomes 5 times 10 to the negative 3 di of t divided by d of t plus 80 times I of t plus, well, that's what we're looking for, which is, I'm going to keep it v of t even though it should be vc of t, but that's okay because this is something we're looking for. Alright, so we have now an equation that describes the circuit, and this equation contains a couple of variables, I and v, and frankly speaking, we're being asked to compute both of them anyway, so you can either write v in terms of I or I in terms of v, but what I will do is I'll just write v in terms of v, basically I'll write I in terms of v because I think it's just more interesting, because I know eventually that voltage across this capacitor should be 100 volts, so, and the current of course should be 0, but I'm just going to do that. You can do it either way. Alright, so that means I'm going to have to realize that I of t is just simply C times dv of t divided by d of t. This is actually coming from this one here, and of course we're assuming that the passive sign convention is hitting the positive here, so we're good. So what we need to do is we need to replace the c with its value, which is 2 to the negative 6 in here. That means the derivative, well, do I need the derivative? Yes, because I need the I of t. I only have I of t in here, so we need the I of t. So let's do the derivative. So what the derivative does tell me is the I of t divided by d of t is just simply 2 times 10 to the negative 6, the second derivative of the voltage divided by dt of squared. So I will basically, whenever there's an I of t, I'll just substitute it with this value, that's this here. Whenever there's di of t, I'll just substitute it with this value. And what I'll end up with is the following. I'll move the 100 to the other side. I'll end up with 5 times 10 to the negative 3 times 2 times 10 to the negative 6, and that's d squared v of t divided by dt of squared, I believe, plus I of t is just simply 80 times 2 times 10 to the negative 6 dv of t divided by d of t plus v of t, and that should equals to 100. So we'll do a little bit of algebra. I'll basically compute what these values are, and then what I will do as well is I'll divide everything by that so that the coefficient next to the second order is just 1, and what you'll end up with is the following. So the equation you're going to end up with is the following: t squared v of t divided by dt squared plus 16,000 dv of t divided by d of t plus 10 to the power of 8 v of t equals simply 10 to the power 10. So that here is the second order differential equation that describes the circuit after switching. Okay, and what we see in here is the forcing function is not 0 anymore, so the solution for that voltage v of t is simply a couple of things. It's a complementary solution and a particular solution. And since the forcing function happened to be a constant, we know that the particular solution should also be constant, and of course that means the second derivative and the first derivative of that particular solution should be 0. So let's find the particular solution. Okay, vp of t. So what we can do is we can say 0 plus 0, these are the second and first derivative, plus 10 to the power of 8 v particular solution t equals 10 to the power 10. that means simply the VP of t, which is the particular solution, is 100. So let me just highlight this because we will need it later. So I found the particular solution for this differential equation in here. So that leaves me here, I need to find the complementary solution. So the complementary solution is the solution for this equation in here, okay? But instead of having it equal to 10, what we do have it equal to is 0, and that makes it a homogeneous equation. And then what we do is we derive the characteristic equation. The characteristic equation is simply s squared plus 16,000s plus 10 to the power 8 equals 0. So what we need to do now is to figure out what alpha is, what omega 0 is. Well, we know that 2 alpha is just simply 16,000. That means alpha is simply 8,000 rads per second. Okay, what about omega 0 squared? Well, it's 10 to the power 8. That means omega 0 is just the square root of that, and that should be equal to, that's 10,000, or 10 to the power 4, also rad per second. So now you can tell me, well, alpha happened to be less than omega 0. That means what we have here is an underdamped response, okay? So we have an underdamped response in here. So what do we do with that? Well, we use the underdamped solution, or also you can also compute the discriminant delta. And delta is just simply 16,000 squared minus 4 times 1 times 10 to the power 8, and you'll end up with some sort of a negative number. And I calculated it, even though we will not be using it, 144 times 10 to the power 6. The idea is it's a negative number, so I have two complex conjugate solutions in this particular case. And before we move on, what we usually do whenever we see that we have an underdamped response, I think we need a D in here. Okay, so underdamped response, what we do compute usually is omega D, which is just simply the square root of omega 0 squared minus alpha squared, which is just simply, you can compute it and you'll end up with 6,000 rads per second. Okay, that's basically that 10,000 squared minus 8,000 squared. That's basically and under the square root, and that will be 6,000. Why do we do that? Because what we have is the complementary solution is just simply e to the negative alpha, which is 8,000 t, beta 1, which is a constant where we will compute cosine omega d, which is 6,000 t, plus e to the negative 8,000 t, beta 2, sine 6,000 t. So that's the complementary solution. Of course, what we're looking for is the full solution, and the full solution is simply v of t is a particular solution. So let me just highlight this here. So that's the complementary solution in here. What we need is the particular solution, which we found out to be 100 right here, okay, plus whatever we have in here, which is 100 plus beta 1 e to the negative 8,000 cosine 8,000 t cosine of 6,000 t, plus beta 2 e to the negative 8,000 t sine of 6,000 t. Okay, and that basically it. But now what we need to do is we need to find what B1 and B2 is, and the way we're going to do it is we need two initial conditions to find them. So let's find these initial conditions. Well, first what we will do is we will need V0, okay, and you know what, let me just find these right before switching. So we can do that before switching. Let me bring the circuit before switching and after switching. So here's the circuit before switching, and just to highlight a few things in here. So hopefully you'll get the I0 is just simply 0 actually, because there's no current flowing through this, because the circuit here is cut, okay? And right that here, just to emphasize, this is a t equals 0 minus right before switching. Okay, and of course what we have as well is the following. So this part in here, okay, is just simply an open circuit in here. Okay, and that open circuit will happen to be plus minus. This is V0 minus or 0 plus, and that's simply the same voltage across the 15 kilo ohms. So technically, we can just compute the V0 is just simply 80 times 15 divided by 15 plus 9. Okay, and that should be equal to pretty much, I believe it should be equal to 50 volts. So that's 50 volts. Okay, and we just computed I0 is just simply 0 amps. Okay, I didn't have to compute it, it's just obvious from the circuit. All right, so going back to the original in here, what we need is we need to use these particular initial conditions to find B1 and B2. So what we have found is V0 is just simply 100 plus beta 1. Well, think about it. E to the power 0 is 1, cosine of 0 is 1. So these here are 1, so that's beta 1. Okay, and in here, well, this is e to the power 0, which is 1, sine of 0 is 0, so the whole thing is 0, so beta 2 doesn't appear. So that's what we have, and we have found out that V0 is 50, that's 100 plus beta 1. That means simply beta 1, which is negative 50. Okay, so that's the one here, so I'll just highlight it. All right, then what do we do next? Well, next we can just figure out dv of t divided by d of t, and we assume that it's at t0. Well, we know, well, based on the equation in here, remember, I mean, we have found out here, where is it? This here. We have found out what this means. Okay, so let me just do that, copy. Well, based on this is the capacitor. Well, actually, we're not going to be using this because this is for the inductor. Well, what I can tell you is the following. I'll write it for the capacitor. So for the capacitor, typically I of t is simply C times dV of t divided by dt. This is for the capacitor. Remember, we had a capacitor in here. Let me just put that circuit one more time. It's this circuit here. So the capacitor voltage in here, remember, so I is here, and of course, like after switching, this is what it appears. So what we have is C dV divided by dt. Okay, so what we're looking for is dV divided by dt. So it simply should be equal, and now forget about t equals 0 for now. That should be equal 1 divided by C I of t, and this I of C, you know, this is the I going through the capacitor, which is the same I of t in here. And passive sign convention tells me, well, the current is hitting the positive, so positive is okay. So let's substitute a few values in here. dV of t divided by d of t equals 1 divided by c, which is 1 divided by 2 to the negative 6 in here, I of t. So if I substitute t equals 0, and this one here, t equals 0, well, that means I of 0. But I of 0 is 0, so that means the whole thing here is 0. Okay, so that's pretty much it. So dV of t divided by dt, if I evaluate that t equals 0, the value for it is just simply 0. So what we can do now is we can go to the original equation that we have in here, the one not highlighted is this one, and we take the dV divided by dt, and we'll end up like, of course, you're going to have to take the derivatives and whatnot, or look at my notes and just find the equation that you should be using. And that equation is simply... equation simply tells me dV of t here, dV of t divided by d of t at t equal 0 should be simply negative alpha beta 1 plus omega d beta 2. That's the equation. That you can, again, you can get it directly without actually knowing by just going and taking the derivative of the first derivative, and that's it, and setting t to be 0, and you end up with this equation. So let me just substitute with the values I know. I know that this is 0. I know that the alpha, I believe it was 8,000, right? Yes, it is 8,000. And I know that beta 1, we just computed it to be negative 50. Okay, and I know that omega d should be 6,000. It's the one with the cosine in here, and you can see it. Okay, so that means here, which is 6,000, and that's beta 2. So one equation, one unknown. Hopefully we should be able to figure out the beta 2 is negative 200 divided by 3, which is negative 66.67. All right, now putting everything together, what we end up with is the following. V of t is just simply negative 50, that's beta 1, e to the negative alpha, which is 8,000 t, cosine omega d, which is 6,000 t, negative 200 divided by 3, or 66.67, e to the negative 8,000 t, sine of 6,000 t, and of course I forgot the particular solution, which is plus 100, because remember there's a particular solution. In this particular case here, we have a particular solution. So that was a complementary solution. This is the particular solution. I just put the particular in here. All right, just a quick sanity check. This should be the final solution for that circuit, at least for V of t. So if we put the circuit one more time in here, when we take a look at it, what do we have? Well, what we have, if we put t equals 0, okay, so that will be 1, this will be 1, so I'll get negative 50. Okay, and when t equals 0, the whole thing here becomes 0 because sine of 0 is 0, so that tells me it's 100 minus 50. So initially I had 50 volts across this, and that's exactly what we got from the initial conditions in here. We got 50 volts for V0. Good. What if we wait it for enough time? So if we wait it for enough time, so this becomes 0, this becomes 0 because e to the negative infinity, e to the negative infinity. So that leaves me with V of t equals 100, which does make sense because after a while, that voltage in here appears in here because there's no voltage drop in here or here. All right, so I think we found out what V of t is. Well, what if we wanted I of t? Well, we can use this equation, okay, which is the current across the inductor. Remember, so I of t is just simply C times dV of t divided by d of t. It's just a simple derivative, so you only have to take this derivative in here and this derivative in here. And again, it's a product rule because you have an e and the cosine. What you do is you take the derivative of the e times the cosine, and then the derivative of the cosine times the e, and then you do the same thing, the derivative of the e times the sine, and then the derivative of the sine times the e. Of course, the derivative of 100 will be 0, and what you will end up with is I of t is just simply, here's the solution that you should be getting, 1.67 e to the negative 8,000 t sine of 6,000 t, and that's an amp for t is greater than 0. By the way, this is in volts. The unit for t is greater than or equal to 0. And let's do a quick sanity check in here. So this is that. So initially what we have is, if I told you t equals 0, well, t equals 0, everything is 0. And that's exactly what we have right before switching. It was 0. What if we wait for a long time? Also is 0, which is good. And this actually end up at 0. So if we plot the voltage and the current, the voltage across the capacitor that is, and the current flowing through that capacitor and the inductor, we'll see the following. So we will see in here, here's the voltage, and the voltage initially before switching was at 50, and then when we switch in here, what happens, like, it will eventually reach the 100. That's the goal. So that's the 100 of the 50. But it actually have some sort of a oscillation because I have a sinusoid and cosine, and that's what you see in here. It actually overshoots over 100. That's what you see in here. Maybe it's slight, but it does shoot over 100. Okay, so it's not a lot of oscillation, but there's some. So it reaches over 100 and then eventually gets to 100, but very quickly. Look at the time in here. Now, these are all in seconds, by the way. So 0.02 or 2 milliseconds or so. Like basically at, let's say, even less than 1 millisecond, we are at the final voltage, which is 100. Now in here, what do we see? Well, that's the current. So the current initially was 0. That's what you see in here. And eventually it will get to 0. That's also here. But it shoots up and down because there's some sort of an oscillation as well. So initial value is 0 and the final value is 0. And the response in here, we got that 0. And of course, it does shoot below 0 as well, as you can see in here, because of the sinusoid. So we only have sine in here. The cosine has a coefficient of 0.